Alright guys, you asked me for a video on our zombie outbreak problems. So here's a new situation. We have a zombie outbreak. It starts with 3 people. So on day 0, the total number of zombies is 3. Okay, each zombie has to infect 2 people each day. So we're going to make a table representing the number of zombies for up to 5 days. So let's think about this a little bit. We have 3 people, and each of them infect 2. Okay, so sometimes diagrams are really helpful in helping us understand what the situation is. And it's also important to know what your table is representing. Our table represents the total number of zombies in the world, not how many we're adding each day or how many new zombies there are. This is the total number of zombies. So here we have each person infected 2 people, or each zombie infected 2 people. So now we have a total of 3, 6, 9 zombies on day 1. So day 1, now we have 9 zombies. So each of these 9 people now infect 2 more people each. So this person has also infected 2 people, and this one has infected 2, and this one has infected 2. So the red is going to represent day 2. So how many do we have now? So we added 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We added 18 new zombies to the 9 original. So now on day 2, we have 27 zombies. And then day 3, do we see a pattern yet? Usually by the 3rd day, we can see a pattern here in what we are multiplying by. Even though we grew by a rate of 2. So the growth rate was 2 zombies per day, per person, per zombie. Our growth factor is the fact that I can easily get this by multiplying by 3 over and over again. So on day 3, we have 27 times 3 is 81, and on day 4, we have 243, and on day 5, we have, 729. So we have 729 zombies after day 5. And you can see that's a factor, the growth factor of 3, because the population is tripling every day. So this means it's tripling each day. So we want to write the equation that represents this, because if I want to find how many zombies there are on day 10, I certainly don't want to have to do this 10 times or keep going in my table. So we have our general equation for exponential growth, which is a equals 1 plus r to the t power. This part of our equation, 1 plus r, is my factor. How much I can just multiply each one by. The rate is the fact that there's 2 zombies per day, and we should notice that when I plug 2 into my equation here, I get 1 plus 2, which gives me my factor of 3. So that's the first part of my equation, how fast it's growing. And A represents how many people we start with, and we started with 3 zombies. So my equation is 3 times 3 to the t power. Having a model, an equation, so when it asks for a model, it's asking you for that equation in the general form a times 1 plus r to the t. Having that equation is really helpful when we want to make some predictions farther on down the road and we don't want to continue to have to make the table. So remember our equation, f of x is 3 times 3 to the t. So I want to know how many there will be on day 14. 2 weeks later, how many zombies will there be? So it's 3 times 3 to the 14th power. So we want to make sure that we use our order of operations correctly. First, we're going to do 3 to the 14th in our calculator. Let's see. We get 4,782,969 times 3, which gives us 14,348,907 zombies on day 14. Basically, at least the United States have taken over, and it's spread to China, Mexico, and down the continent. So now the next thing we look at is how can we decide or figure out how long it takes to get for there to be 5,000 zombies. So we're looking at solving this equation. 5,000 is equal to 3 times 3 to what power, x or t? And I want to know what x has to be to make that true. So we're going to use our guess and check method. Well, we know that after 14 days there's 14 million, so we can go significantly lower than that. Let's try 10 days. How many zombies will there be after 10 days? 3 to the 10th power is 59,000 times 3, so we're way too high. 177,147. So what about day 7? 3. My calculator just closed on me. 3 to the 7th times 3. So day 7, 6,561. So day 6, 3 to the 6 times 3 is 2187. So our answer has to be somewhere between 6 and 7. So we're just using guess and check, but as we move on and learn about logarithms, logarithms are the key to solving this equation without having to use guess and check. So let's try 6.5. 3 to the 6.5 power is 1262 times 3, so 378, 3,787.9. So we need to go higher. 3 to the 6.7. Let's try 6.7. 6.7 gives me 4,718.82. Let's try 6.8. Oops. 3 to the 6. 3 to the 6.8. So I'm doing this all in my calculator right now. 5. So 6.8 gives me 5,266.79. So now I know it's between 6.7 and 6.8. So I'm going to try 6.75. So 3 to the 6.75 power times 3 gives me 4,985.2. So I'm getting even closer. So here, if I was asked for 2 decimal places, we could pretty much say between 6.75 and let's see what 6.76 gives me. 3 to the 6.76 times 3. 6.76 gives me 5,040.35. So we get an answer somewhere between 6.75 and 6.76. And of course we can keep adding decimal places to get more accurate, but we don't want you to spend hours on this question on the test. We just want you to get close. So we would say at approximately 6.75 days is when we reach the 5,000 zombies. So the next thing we asked you to do, and again we kind of talked about it already, was to identify the factor and the rate of growth. Our factor again was the 3, the fact that it's tripling every time. And that was my trick to making the table work after I used my diagram to show how there was. Okay, so once again, we'll look at our equation. We had 3 to start with. Each day they were doubling, they were infecting 2 people. So you were tripling the population. So the rate is how many each zombie is infecting each day. So that's 2. The factor is what we multiplied by. So it's 3. We started with 3, we ended up with 9, 3, 9, we said 27. So this times 3 is our factor. And again, you can get that from 1 plus r is equal to your factor. Okay, then the next thing we looked at was a cure. What if there was a cure and say 1/4 of the population, that was the one you had on your quiz, 1/4 of the population is cured every day. Or so let's say we start with 20,000 zombies. And for whatever reason, they can only cure 1/4 are cured each day. So on day 0, we end up with 20,000 zombies. That's our starting point. Now, if 1/4 of them are cured, that means when I do 2,000, or 20,000, sorry, times 1/4, I get 5,000. This is 5,000 are cured. Our table is the total number of zombies. Our table is not the number of zombies that get cured, so this 5,000 does not belong in this table. The 5,000 is how many we cured, so we need to put how many zombies are left in our table, which for this day would be 20,000 minus 5,000, which is 15,000. So I have 15,000 left. Now that I have 15,000, I can multiply that by 1/4, and that will give me how many are cured again. Now, some of you found an easier trick to this because you don't like the multiplying and then subtracting and the multiplying and subtracting. This is 3750, and then 15,000 minus 3750 gives us how many we have left on day 2, 11,250. And we have to keep going that way, multiply by 1/4, subtract from how many there are. That's how you get the correct table. But how do we figure out the factor? It's not as easy to look at as just saying, oh, I multiplied by 3 every time. We don't generally see that when we're looking at fractions. So the question is, if 1/4 are cured, how many are not cured? Because that's what goes in our table. Oh, how many? Well, that's 1 minus 1/4, which is 3/4, which is your factor, because the rate is 1/4. So you can actually get the same answer if you do 20,000 times 3/4, you get 15,000. And if you times that by 3/4, you get 11,250. And then we can continue that. So your equation for a cure type of situation, a decay situation, your general equation is 1 minus r to the t. And it's 20,000 times 1 minus 1/4, which we said is the same thing as what we get when we look at for our factor, how many are not cured, to the t power. So my equation is 20,000 times 3/4 to the t. And now you can use that equation to estimate how long it's going to take to get everybody cured. And as long as you get a number less than 1, that's at the point where we are cured. But you have to make sure you are using your order of operations in your calculator correctly. Okay, so I think that's it for the zombie problem. I hope this helps.